In this part of the section, we'll consider the gradient descent method for partially definite linear systems. Once you try to solve a partially definite linear system, you may use the conjugate gradient method rather than the gradient descent method. So the gradient descent method is rarely used for solving positive definite linear systems. However, here we'll consider the method to understand it more thoroughly. See the definition. A is a square matrix, and the matrix is said to be positive definite if this term X transpose AX is always positive for non-zero X. If A is symmetric, then A is positive definite if and only if all eigenvalues of A are positive. So for symmetric positive definite system, the eigenvalues are all positive. The symmetric positive definite system can be formulated with this minimization problem if eta is defined to be here in this way. Then the solution of this minimization problem is the same as the problem. You may check it easily. Once eta is the minimizer, then the derivative with respect to eta must be 0. Once you take the derivative, actually the gradient, then from here, so the gradient of f is same as, okay, that is now a eta minus b. By setting it 0, we reach at this problem. So they are the same. Okay. For the algebraic system given here, the Kirchhoff subspace method can be used in this form. Iteratively, we try to update the solution. xk plus 1 is xk. From old one, we try to update by using this correction term. In this case, pk is the search direction, and alpha k, usually this is positive, is the step length. And the gradient descent method is one of the Kirchhoff subspace methods. The different methods differ in the choice of a search direction and the step length. In this subsection, we'll focus on the gradient descent method. For other Kirchhoff subspace method, you may go to this reference. Okay, let's try to derive the gradient descent method for the linear system. For the functional f, the gradient is this one, and then Hessian, the second derivative, is the metric A. Now, by using the Taylor's formula, and xk plus 1 is same as that one, now we can expand in this way. Now, in fact, the Hessian is same as the metric, and if the metric is bounded, so usually it's bounded, then we can write in this way. Here, the same A, as in the last subsection, the goal is to find the search direction and step length such that at new approximate, the function value is smaller than the last one. Once we choose, here pk such direction, and to be negation of the gradient of f, then that portion will be negative, and when the alpha k is sufficiently small, and now already A is symmetric pi definite, and here this is always non-negative, in fact positive, so that once it is smaller than 0, then the goal will be achieved. So the choice is, now pk is negative of the gradient, and already we know the gradient a eta minus b, and negative it is b minus a xk. And for that term, usually we are using rk, which is the remainder, the residual. Okay, so pk will be chosen as the negative gradient. That's the gradient descent method. Now we have to choose the step length alpha k. For solving linear system, usually alpha k will be chosen from this optimization problem. We'll try to get alpha k such that this function has a minimum value. Now, by using calculus technique, we can decide alpha k. And we see this one as a function of alpha, and we can differentiate it with respect to alpha. Then for that one, we have here, and now by using the chain rule, first we try to make the derivative, so it is gradient with respect to that one, and then here for this term we make alpha derivative, then that is pk, so we reach at that one, and after that alpha is replaced by alpha k, so we have this one. Now we are using the practical terms from this gradient. Now rather than eta, we put the term here xk plus alpha k pk. Then we have this one. So this, from this one we can decide alpha k. So alpha k is the same as, okay, that is negative of the residual. So we can move this one to the other side and divide by that constant. So we reach at this one. So this is used for various clear-up subscript method. That is a kind of a universal way of getting alpha k once you choose the search direction. So that depending on your search direction, here alpha k will be decided. But that is now an optimal choice. Okay, here we have the gradient descent algorithm, and with the initial value x0 and epsilon, the stopping tolerance, we first compute the residual for given initialization. Now alpha k will be computed in this way. Now pk in gradient descent method, pk is rk. So here alpha k can be obtained in this way, and we update the iterate, and then we try to get here residual. Once the residual is bounded by the tolerance times original residual, then we can stop the iteration. Now here the residual rk plus 1 is defined in this way. and that way, b minus a xk plus 1. But rather than that one, we try to use this equation. The reason is here. Now, when you implement this algorithm, then in each iteration, you compute this one and save somehow. Okay, for example, that is saved into a vector q. Then you can use this one here again, so that for each iteration, you can do only one metric vector computation. In this algorithm, most expensive portion is the metric vector computation. But if you try to use this definition, then you have to do one more of the metric vector computation. Rather than that, we are using this one. Now, this one and that one is the same. You can prove it quite easily. And I leave this problem for you, so you can figure it out yourself. So here the main, the purpose of using this formula is to save the computation. Okay. Now for the gradient descent method, we may analyze its convergence. Once A is invertible, then for invertible matrices, the condition number is defined in this way. Here, norm of A times norm of A inverse. Of course, this norm is a metric norm, and that is the definition. And when the metric is symmetric pi definite, then condition number becomes here the ratio between the maximum eigenvalue and the minimum eigenvalue. And that is the condition number for, of course, here we are using 2 norm. So condition number 2 norm. Okay, here we have a theorem, convergence of the gradient descent method. The GD method converges satisfying this inequality. So at the case, after case iteration, the error is bounded by here this portion times original error, so that the number of iterations required to reduce the error by a factor of epsilon can be found in this way. So we can get this one from this inequality. For example, it's bounded by epsilon, and this portion can be solved by, of course, over the, in fact, epsilon times x minus x0, like that, so that we can cancel these two and then solve for k, then we can reach at that one. So it is the k, the required number of iteration is order of condition number of A. So that's the reason here the number of iteration required is large for gradient descent method. But if you are using the conjugate gradient method, in fact, the k, the required number of iteration is around the square root of the condition number. Usually, the condition number is larger than 1 or equal to 1, but most cases, once A is in Rn times n, then condition number of A is, many cases, order of n squared. So that's the reason this one is large, but for conjugate gradient method, it's way faster. And so we know the gradient descent method is slower than other methods. However, when you are solving the optimizing the function, the cost function of the machine learning problems, then in most cases, the gradient descent method is the choice because it is simple. And once you choose the step length nicely, then you can get quite good convergence, and along with partial updates. So practically, people are using the stochastic gradient descent method for machine learning algorithms. Okay, that's the end of the section and end of the chapter. Thank you.